All right. Time to begin. First, let me remind you that exam number 2 is tomorrow, or Thursday rather, week. There are 4 questions on it. Total mark will be 200. And then you can earn another 30 marks from the take-home part of the exam. Question?
I was wondering if you could elaborate a little bit more about how the take-home works. It's mandatory, but does it add to your initial score, or is it part of your total score?
In the first test, you were getting 180 for the in-class part of the exam, and then you got 20 towards the 200 total for that exam on the take-home part. This time, you're going to get marked out of 200, full 200 on the in-class exam, and then part of the graded homework settings will be the take-home part for that exam. Yes.
So is anything on the test going to be anything we haven't covered yet, or have we covered everything that will be on that exam?
The question is, what will the exam cover? Everything up to what I do at the end of this Thursday could be on the exam. Let me remind you also that we have tutor hours on Mondays 10 to 12, Thursdays 9 to 10, Fridays 10 to 11 and 1 to 2 in Math East 241. I'm available tomorrow, Wednesday at 7:15. Also at 8 o'clock on Thursday. You also have your office hours for your TA, and you also have the TA recitation sessions themselves to ask questions. So please take advantage of all this extra help. Right. So now we're coming to the final part of the course, and that is to do with the analysis of systems, in this case second order systems, namely we have 2 dependent variables, x and y, and their change is given by 2 equations. We call them 8-1. dx by dt is f of x, y, and dy by dt is g of x and y, because the equations themselves don't contain the independent variable t explicitly. We call these equations autonomous equations. We're going to look at methods for analyzing, for understanding the behavior of systems described by such equations. Some examples. For instance, this mixing example, if we have 2 tanks, tank A and tank B, x of t is the number of the number of pounds of salt in tank A after t minutes. Y of t is the number of pounds of salt in tank B after t minutes. We start off with perhaps some initial concentration of salt in tank A and tank B, but the influx, there'll be 2 gallons a minute coming in. It will contain, each gallon will contain 1 pound of salt, so it's a concentration of 1 pound per gallon. Then we pump from tank A to tank B at a rate of 3 gallons per minute through this valve here when it's open. And then there's a return feed from tank B to tank A at the rate of 1 gallon a minute, and then an output from tank B at the rate of 2 gallons per minute. So the concentration, since the volume in to tank A is 2 plus 1 minus 3, the volume input per minute is 0. Therefore, the volume stays the same, 20 gallons in tank A. Similarly, in tank B, we have 3 gallons a minute coming in, 1 going out this way, 2 going out that way. The net gain or loss is 0. So again, we have 10 gallons here in the second tank B for all time. The concentration in tank A will be X over 20. That's the number of pounds per gallon at time t. The concentration in tank B will be Y over 10. The equations then, the increase in the number of pounds of salt per minute is the 2 pounds coming in every minute. Then you have, through this valve, 3 gallons going out, each gallon carrying X over 20 pounds of salt. And so we have minus 3X over 20. And then through the return valve here, we get plus Y over 10. 1 times Y over 10, 1 times the concentration. For tank B, the input is 3 gallons a minute, each gallon carrying X over 20 pounds. So that's the number of pounds per minute coming in. And the number of pounds per minute going out is 2Y over 10 plus 1Y over 10, making a total of 3Y over 10. Now these equations happen to be linear in X and Y, but the methods I'm going to be showing you don't require things to be in fact linear at all. But nevertheless, we will start by analyzing this system using the JODE software. I'm going to show you now the results of these 3 cases. So the second case essentially is, this is meant to be a rabbit, and this is meant to be a fox. It looks more like a javelina, but anyway, it's this is a predator and this is the poor prey. The prey, so X is some measure of the number of prey at time t. Maybe we'll measure t in days or hours or whatever. Y is the number of the predator around after a time t. A fairly good model for the interaction between the predator and the prey is as follows. The prey will exist on the environment. So roughly, dx by dt, his population, his numbers will grow exponentially according to this linear term. Dx by dt will be proportional to the number of prey present. I've just taken, for convenience, these coefficients to be 1 all the way around. We can always reorganize things so that we can almost clear out all coefficients except 1, as you'll see a little bit later. But for the purpose of this first lecture, we will use very simple coefficients. So the poor rabbit gets eaten when he meets a fox. The probability of him meeting a fox is roughly proportional to the number of rabbits present times the number of foxes present. So that's the reason for this term here. On the other hand, the poor old fox, left to himself, if there's no rabbits, his population will die out. That's the reason for this term here, minus y. But he is sustained when he meets the odd rabbit, and so we have therefore the term plus xy here. So here's two equations. dx by dt is x minus xy. dy by dt is minus y plus xy. And the goal is to try and solve these equations. Or actually the goal is not just to write down analytical solutions, because you sort of can in this case, but they're so complicated that you don't learn much from them. Our goal is to try and understand what's happening in this interaction, to try and understand the behavior of x of t and y of t as time evolves. The final example is a simple pendulum. We have x is the angle here of displacement of the pendulum from the vertical, and the pendulum is going to swing backwards and forwards like this. So x is this angle. The forces, so dx by dt is y, that's the angular velocity. Then the Newton's equation in this direction will tell us that d2x by dt squared, or dy by dt, is the sum of the forces, and in this case the forces acting will be a friction, probably due to the hinge, and the gravity force, which will be mg times the sine of x. Now I've just taken out the coefficients, the mg over l, or the g over l term here. I've just made it for convenience here to be 1. We can more or less always choose units to arrange that. So this is the third example. Now, before, when we met the pendulum, we were considering very small oscillations. So we replaced the sine x by x. Because for x, actually x up to almost 30 degrees, sine x and x aren't all that too much different. Okay, because what? X at 30 degrees, 1 radian is 57. So x would be 30 over 57 in radians, and the sine of 30 is a half. So 30 over 57 and a half, it's not too different. So even up to angles as much as 30 degrees, the approximation of sine x by x is not too bad. But we want to look at penduli that really swing and maybe even go over the top. So we want to understand all the different kinds of behavior that we get in such penduli. So what we're going to do today is explore. We're going to use the software, this wonderful program, the JODE, just to put the equations on the program and look at what happens. And then we'll play around and we'll try and come up with some understanding of what's going on, and we'll try to find out what questions should we ask about this system, and how might we go about answering these questions, either using the software, the simulations, or maybe in some cases, as I'll show you, we'll be able to use some analytical methods. Now the first thing I'll draw your attention to is as follows. Equilibrium points. Equilibrium points are points xe, E for equilibrium, ye subscript, such that F and G are both 0. Okay. The equilibrium points will play an important role in our understanding of the behavior of the system. For instance, I'd like you to spend a minute, calculate what are the equilibrium points for example number 1. You're doing it in your head. Right? Good. Because I'm going to ask you now in a minute. Are you becoming hypnotized by this, or do you have the answer already?
I have.
Yeah?
Yeah. Well, I have y, I think.
Y is what?
I think it's 10.
Very good. And if y is 10, from here, what's got x got to be? 20. So the equilibrium points for this example are xe equals 20, y equals 10. Actually, can anybody give me a reasonable, rational explanation of that equilibrium point? Right, but remember, this is the number of pounds of salt. So why is 20 pounds of salt an equilibrium point?
Concentration of each tank is equal.
Very good. You can see after a sufficiently long time, imagine the stuff coming in as blue, and this starts off green, and this starts off yellow. After we flush the system for long enough, what's the color in each of the tanks going to be? Same as what's coming in, blue. So you'll have all, this will have a concentration of 1 pound per minute, 1 pound per gallon, as will this. But this is 20 gallons, so there'll be 20 pounds. So it's the final state of the system is the equilibrium in this case. Question?
So how did you solve for the equilibrium points again? You said
Yeah, I put this equal to 0 and this equal to 0. If I put this equal to 0, I have x equals 2y. Put x equals 2y in here and solve that equation for y. Okay? These are two straight lines in the xy plane that cross once. Okay, and they cross at 20 and 10. How about this? What are the equilibrium points here for the predator-prey? There are two of them now. Yes.
0.
0, x is 0, yeah. No, because if x is 0, you've made this 0. Now if x is 0, this is gone. So in order to make both f and g 0, what does y have to be? 0. So 0, 0 is 1 equilibrium. And what's another one? 1, 1. Okay. What we're going to find is, in some sense, the trajectories in the xy plane will be organized by these equilibrium points. In a way you'll see. How about this guy? What are the equilibrium points here? Certainly y has to be 0, because to make that 0, and if y is 0, what makes sine of x 0? Yeah, you could have 0, 0, pi 0, minus pi 0, 2 pi and 0, and so on. Any n pi and 0 will be an equilibrium point. Okay. So, the first thing we're going to do is look at the behavior of these three systems and then see what role the equilibria play in organizing the system. Before I show you the first example, what's a natural question to ask about an equilibrium point? Very good. Is it stable or unstable? Remember, there are two kinds of stability. The idea being, if we perturb the system a little bit away from xe, ye, will the system, for all time, will the new x and y as a function of t always stay in the neighborhood of xe and ye? If it stays in the neighborhood, if it starts close and stays close, we call that what kind of stability? Lyapunov stable. So that's like a pendulum which isn't damped. Here is the position 0, 0, or 2 pi 0, or minus 2 pi 0, okay, is right down like that. No damping. I give it a little kick, and it just swings backwards and forwards, but stays in the neighborhood. The velocity is very small, and the angle is very small. So that's Lyapunov stable. Now, if we have damping, the equilibrium can be asymptotically stable, or it could be unstable. But if the equilibrium is such that when I give the system a little kick in the neighborhood of xe, ye, and as time continues, it not only stays in the neighborhood, but actually returns to xe, ye as t goes to infinity, then we call that asymptotically stable. Okay? But, you know, the interesting thing is we're going to find that the unstable points play as important a role in organizing the system as the stable points. We were going to find that this position up here in the pendulum, which is like pi and 0, in other words, 0 velocity, and the angular deformation is pi, this position, even though if you give the thing a little kick, it'll swing this way or this way, it's unstable, but nevertheless, these are very important points in this plane we call the phase plane, the plane of x and y, and we draw the curve in that plane as t evolves. You see, as t evolves, x will change with time and y will change with time. And if we plot the pair, x, y, as time changes, we'll get a trajectory in this plane. Now we're going to look at, in fact, in this case, we're going to look at x of t and y of t individually, x is function of t and y is function of t, as well as what the trajectories look like in the xy plane. Okay, so now I've got the JODE up here, and I've put in the equation here. dx by dt is 2 minus 3x over 20 plus y over 10. dy by dt is 3x over 20 minus 3y over 10. I've given it enough time, 50 units, so as it will actually have time to reach this equilibrium. Because the equilibrium is 20, I've taken the range of the x from 0, it can't be less than 0, it's number of pounds, up to 40. And I've taken the range of the y to be 0 up to 20, because I want roughly that equilibrium point to sort of sit in the middle. All right, so now let me draw this down a little bit so that we can see what's going on here. Now I'm going to just start the system. Let's start the system, say, at say out here. Okay, so we're starting the system at y equals 18 and x equals about 2. Oh, so that's the trajectory. This is the trajectory in xy. I'm using the Runge-Kutta 4 with a time step 0.1. So what has happened is this trajectory, as time goes on, it starts up here and it comes down and it ends up at this point is 20, x equals 20, y equals 10. Okay, let's start over here now. Now, it's very interesting. It starts up here. It seems to come into this same straight line. This is again the point 2010. Let's start down here. Oh, I hit it. There you go. There we go. So we can see that almost all initial conditions, in fact, all the initial conditions end up, after a long time, at the point 2010. Now that's what your understanding was. So it doesn't matter how green and how yellow this was to start out. In the end, everybody is going to be blue. And we can see now it comes along here in this very interesting direction. Now that's one thing we might ask. Why does it always end up coming into the point 2010 along that direction? Well, we don't know maybe quite yet, but we will learn. What we're going to be looking at is we're going to be looking at the behavior of the trajectory near here, and what we're going to find is roughly the following. That the difference between x and 20 and y and 10 will be given by two terms. It'll solve actually a second order homogeneous equation, which is linear because we start near the point. So we make the deformation from xe and ye small. And we're going to have a solution e to the r1t and e to the r2t. Now you can look at the notes. The lecture notes 22 to 30 has this calculation carried out. And you're going to find that the r1 is minus 9 plus root 33 over 20, or 40 I think. And the r2 is minus 9 minus root 33 over 40. But clearly, the exponential, both are decaying exponentials, but the faster decaying exponential very quickly disappears. So the system comes into this kind of trajectory here, and then more slowly approaches the fixed point 2010. So this guy, so is the equilibrium point 2010, would you say it's stable? Is it asymptotically stable? Yep, it is. What do we call the set of all initial conditions which are attracted to an asymptotically stable equilibrium point? Basin of attraction. What is the basin of attraction here? Everything, right. Not every x, every y. Doesn't matter what colors you have here initially, you will always end up at the equilibrium point 2010. Okay, now in this case, because this is linear, by eliminating, you can eliminate the x, say, out of here, or eliminate the y, solve for y in terms of dx by dt, the 2 and the 3x over 20, substitute it in here, and you'll get a second order linear equation which you can actually solve. So in this case, we can use machinery we've already used before to actually write down an explicit expression for the solution. But actually, you know, the expressions are kind of complicated. They have these numbers minus 9 minus root 33 over 40 and everything. So it's much better actually to understand things from the picture. Now if you want to put in the slope field, we just press the slopes, and there's all the little arrows that tell you what the dy by dx, what the slope is of essentially the ratio of g to f. We'll come back to that point later. Now, so end of that example. So now I'm going to do another example, the predator-prey. So we'll dx by dt is x minus x multiply y, and dy by dt is minus y, then plus x multiply y. The time let's leave the time the same. Now the x, the number of rabbits, since we had the equilibrium point was 1, 1, let's go up to 3. Let's go up to 3 on both for x and y. So imagine the units are 1,000 rabbits or 1,000,000 rabbits or something. So we're going 0 to 3. So we'll use the same thing. Now here is the xy plane, and this is the slopes field. So actually you can actually tell from here sort of what's happening. Here's the point 1, 1, and you can see the arrows are telling you things go around like this, the trajectory as x and t progress. Let me actually, first of all, we'll get rid of the slopes, and let's take a look at the solution. Let's take a look at the solution y versus t. So y versus t. And let's start, say, up here. Oh. Now, let me actually put in a couple of initial conditions here. I'll clear here. I'll put in x will start out at point, I think actually a nice one would be 0.36, and y I'll do the same, 0.36. Okay, and let's see what things look like here. So, yeah, why isn't it running? Oh, because I have y versus, no? That's okay. Well, let me go back to the x one again, and let me put in the slopes, and okay. So what I'm going to do here, let's clear again and just get rid of things here. I'm going to start at the 0.36, and then I'll draw the x versus t, y versus t. So I'll start about here. That's a little bit too dramatic. No, a little bit too dramatic. Let me make it so it actually fits in the thing. So I'll say start here. That's a nice one. Okay, so now the arrows tell you, as time progresses, which way x and y go. For instance, as time goes on, the trajectory moves this direction. How do we know that? For instance, dx by dt in this example is x minus xy. So if y is less than 1, so if you're below this here, if you're below this, the dx by dt is x times 1 minus y. It'll always be positive. So as t increases, x will increase. So the arrows below y equals 1 will always be down here, will essentially go this way, whereas above y equals 1, the arrows will go the other way. So here's what happens. This guy starts off at x is 0.39, y is 0.58 or 0.53. So say we have 39 rabbits and 53 foxes in the field, or actually 390 and 530 if we're in units of 1,000. So what happens? Well, at first, both the number of foxes and rabbits decreases. It decreases till you get to the lowest number of rabbits here, or foxes rather. The number of rabbits is increasing, the number of foxes are decreasing. Why? Because there is not enough rabbits, there's not enough for this to overcome the negative y. But now the rabbits start increasing and increasing and increasing and increasing. And now, once the rabbits get up to here, okay, once the rabbits have gotten this far, now there's so many x's around 2.5, that the 2.5 times y overcomes the minus y. So now the foxes really start to grow. They have been growing from here. Once the x crosses the 1, once the x crosses the 1 position here, the xy is bigger than the minus y for the foxes, so the foxes start to grow. And the foxes keep growing. And now they're beginning to eat into the rabbit population. The rabbit population went up this far. Okay, and now the number of rabbits getting ate is more than they're producing. And so the foxes are happy as clams. And the fox population is increasing, the rabbit population is decreasing till it gets way up here. Okay, but now the trouble is there's too few rabbits. We're past the x equal 1 again. So this guy is no longer as big as this guy, and now the foxes start to decrease, and you come down and repeat the cycle. But it's quite amazing that you seem to get a periodic solution. You know, it goes in a, for instance, if I start here, you see, all the trajectories, in fact, just run around this 1-1 position. Okay? So, the 1-1 here, what kind of stable is that? Lyapunov. You start near, you just stay near for all time. You have these periodic solutions. So let's now, let me just clear this, and I just draw the curves, what they look like, so that for the first case. So let me do this case again. So that's this case. Now let's take a look at what the x versus t and y versus t looks like. I'll get rid of the slopes field. And now we'll draw y versus t. And so that's the population of the foxes. Now the population of the rabbits, if I put in the x as well, you can see they lead the foxes. So this is x versus t. So the rabbits and the foxes start here. The rabbits immediately increase because the xy is less than the x. So the rabbits are exponentially increasing here. The poor old foxes, because this is less big than this, are still decaying. But you see now, once the rabbits get up to enough rabbits, then the foxes start to grow again. Here's where the xy beats the minus y. And they start to grow, and you can see that there's just a lag. The solution is periodic. X versus t repeats itself periodically at a kind of a, what's the period is roughly for the foxes would be this distance here in time. It's the same period. So you get this periodic solution with the fox population lagging the rabbit population. Now, if you were to, say, come along and you happen to sample the populations, say around this point here, say around this time, in this time interval, you would think, God, the foxes and the rabbits are dying out. You know? Because both the number of foxes here are here, and the number of rabbits are here. There's not terrible many of them. But it's just part of a cycle that will take off again and cycle like that. So one has to be careful jumping in and interfering in situations where there are these natural cycles. Okay, now how about this point here, the 0, 0? Let's go back now to the XY picture. Let's go back to the y versus x. I'm just taking out that. So this is the y versus x picture. How about, what do you think the 0, 0 point is? Who thinks, is that stable or unstable or what? It's a very interesting kind. You think it's stable? No, because if we start near, let's start here. Well, this is going to go on a huge cycle. It's going to go all the way around. So if you start here, it's going to increase and go way out and go up way and come back down here. Okay? So I will just go, I won't go quite as close to the origin. But there you see, this cycle will do this, this will come like this. So what's interesting, however, is that in one direction, if I start here, I go away along this direction, but actually then I end up coming back in along here. So if I give the perturbation up here, before it'll go away, it'll actually come in first towards the 0, 0, but then take off. So it's unstable, but it's a very special kind of unstable point and a very important kind of unstable point. We call it a saddle point. A saddle point. And it's got one unstable direction, namely the x's, but one stable direction, namely the y. Because look, near x and y equals 0, the equations become dx by dt is x, and dy by dt is minus y. So the y's decrease, but the x's increase. It's unstable because if you start near any point near x, y equals 0, 0, you're going to go away eventually from it. It's called an unstable saddle point. And we're going to find, particularly in the next example, how they also organize the trajectories. Oh, question.
I just wanted to be clear. 1 and 1, or the point 1, 1
Yeah.
indicates when there's one rabbit and one fox. Right?
1,000 rabbits, 1,000 foxes, yes.
All right.
So in that situation, roughly each time the rabbits produce, the foxes eat them. And so both this equation is satisfied. This stays 0 and this stays 0. So one fox dies off, but there's one fox produced because we could feed him.
So my question is, what if there's just one rabbit and one fox, then they both die off? They can't reproduce themselves.
Yes, that's true. Once you get into discrete, the discrete numbers, of course, we really have to think of x and y as fractions of large numbers. Okay, you're quite right. If these equations aren't valid for just one fox and one rabbit, you know, so it's really thinking of x and y as proportions of fairly large numbers like million or thousands. Now, one of the interesting things I'm going to have you do before the end of these lectures is actually put a little bit of saturation, a minus x cubed for the rabbits, or minus x squared, and then another hunting term. And then we're going to analyze what happens in that situation. Then the nature of these fixed points will change slightly. And so I'm going to ask you to organize an environment, how to organize how many hunting permits you give out in such an ecology so that you don't destroy either population. And it's tricky enough. You'll see it's subtle enough to try and keep the populations, both populations going. Okay, so now let's do the final example. But you can see this. Now you can put in your own equations. You were going to get me some equations for chemistry, and other people were going to get me other equations. You can now put in your own equations. Actually, you can find software to do 3 equations, 3 first-order equations if you want, but for this class we're just using 2 dependent variables. But there's lots of cases in electrical engineering, a thing called the van der Pol oscillator. You guys might want to do that before we do it in class and analyze what happens. So that you can sort of get a good picture, you know what's happening. This is the way, as engineers, basically, you're going to essentially go from a model to, you're going to put it on you're going to use a software program to analyze what the model is telling you before you're going to go to a differential equations textbook and find out which method to use to write down an analytical solution. So it's very important to get used to this exploration business. All right, now our last example. This is going to be y. y, and now I'm going to actually allow for, if I put in e equals, I'm going to start off with 0, but I'm going to let it be something in a minute. So it's going to be minus e times y minus sine x. Okay, so now I'm going to I'll take the time interval to be the same, but now the x can go both sides. X can be this way and this way. So, and you know, if it's going to go all the way over the top, it's 2 pi. So I think we'll maybe make it 10, minus 10 to 10. So that'll get in lots of different orbits to 10. And we'll use minus 3 to 3 for the y. So remember what the y is. The y is the angular velocity of this swinging pendulum, and the x is the angle it makes with the vertical. So let's submit this again. And okay, we'll clear the thing here. All right. Now, let's start by having x equals 0, and I'm going to give it a smack. So I'm going to give you a positive y. In other words, I have the pendulum hanging here, and I give it a kick. Okay? So I'll start up here around here. So that's the orbit. So you get this periodic solution. This is what you expected. You gave it a kick, it went up to the positive x direction. So it goes around in this direction, because up here, on this half of the plane, y is positive. Therefore, dx by dt, which is y, is positive. Therefore, as t increases, x increases. So we go this direction. X increases. Then when you get down here, what you've gotten to is you've gone up here. The x has gone as far as it's going to go, and now it's going to start coming back. So now the y, the velocity, is in the other direction. It's negative. And now the x comes back to the 0 position, so it's back to the center position. Then it goes out this side to the negative maximum position, and then swings back to where it was. So there's no damping in this circuit. Now let's say we'll start near the top. Okay? So I'm going to give it a bigger bang. So I'm going to give it a bigger bang. Ooh. It almost gets up to this is almost pi. See, that's 3. 1, 2, 3. So this is almost pi. So the equilibrium points are 0, 0, pi 0, minus pi and 0, and then 2 pi and 0, and minus 2 pi and 0. So let's take a look here. Let's just go past here. I'm just going to go tiny bit above this. Oh, look what happened. So what do you think happened? So I gave it a bang, okay? So in the first case, so in this case here, tell me what happened. So started up here, gave the pendulum a big hit, starts at the x equals 0. It goes up to x equals almost pi, but doesn't quite get there. So yes, exactly. So it goes up to here, doesn't quite make it, swings back around to here, swings up again, swings up like this. Now, in the second case, when I increased the bang I gave it, what happened? It went over the top, you see? And it gets slow at the top, but falls over. There's no damping, so it keeps on swinging, swinging, swinging forever. You can see it here. You give it a big kick, it goes up to pi. This is pi. It's at its lowest velocity here, but it still has a positive velocity. So it goes over the top and just repeats itself. Okay? Now, for instance, supposing I was to start out here, you see, we're getting around the 2 pi 0. Or if I start here, around the minus 2 pi 0. Or if I start near here, you see, I stay very close. So you can see this whole phase plane, the trajectories here, are organized both by the equilibrium points which here are at the centers, but also these guys, these saddle points. Because if you start near the saddle point, it depends whether you're slightly this way or slightly this way. If you're slightly this way, you fall back. If you're slightly this way, you continue on over the top. So these guys, as we'll see, are unstable saddles. These guys are what kind of stable? Lyapunov stable. Now let's add a little damping. Any questions on this? Okay. Let's give it a good kick up here. See? Now it's just flying over the top. Let's give it a good start down here. Now it's flying in the other direction. Okay? So this whole, we call this the phase plane. This can be captured by essentially just solving, or just numerically solving these equations. All right, so now we're going to put on a little damping. So I'm going to make E equal, let's say 0.2. Okay, now I'll submit here. Now look what's happened. Well, it's maybe a bit confusing, so we'll start them off here. We'll start here. I'll start the same way as I did before, roughly here. Now you see what's happening. Okay? I gave the thing a bang. It went up quite a long way. It falls back. But each time it comes, it's slightly less and less each time, the swinging, because of the damping. And eventually it oscillates its way all the way back to here. So now is the 0, 0, what kind of stable is it? Asymptotically stable, because not only if you start near, do you stay near, but you eventually go back to 0, 0. What do you think will happen? What do you think is going to happen if I start it slightly higher, say at the 2.5? Any guesses? Very good. Who said this? Yes, it'll swing over the top once and maybe twice even. Well, let's take a look. Let's take a look. No, it didn't. It got over the top once. You see, it got over the top once, but then it didn't have enough oomph to get over the top again, and it comes back into the 2 pi 0 position. So you gave it a bang. It managed to get over the top the first time, but then didn't quite, and then settles there. Okay, so all these guys now change from being what we call centers, that's the Lyapunov stable points without damping, into asymptotically stable spiral. We call these spiral points for obvious reasons, because the trajectory spirals in to the 0, 0. Okay. So, are there any questions? Do you think now you can play yourselves with these examples? I'd like you now to try. Okay? And maybe take some other examples and see what interesting things you might be able to find. Now, the last thing I'm going to do today is set you up, remind you of some mathematical machinery that we're going to need to analyze what happens not at these equilibrium points, but near them. It turns out that near the equilibrium points, we actually can use all the stuff we learned in the last 6 weeks to say exactly what happens when we start near these equilibrium points. So, whereas the computer, the simulation, allows us to start a long way away and watch what happens as time evolves, in this case we're going to start near here, and find out what happens. We're going to start near the pi and 0 solution and analyze what happens. But we need a little bit of machinery. And the machinery we need is machinery that you guys are very good at, because you've taken Math 129. And in Math 129, you learned Taylor series.
Yay!
Yeah, all right. Mostly groans, but a few cheers. That was good. So what I'm going to be asking, you see, I'm going to say, look, supposing I'm going to start x of t near its equilibrium point. So I'll call that capital X. So capital X is a little perturbation away from the equilibrium point. And capital y of t, I'll say is ye plus big Y of t. Now I will imagine that big X and big Y are small. Big X and big Y are small. So now I'm going to try and approximate what does f of x and y, which is now xe plus capital X, and ye plus y, what does that look like? I would like to write that as a Taylor series in capital X and capital Y. Now, in 129, you learned the Taylor series for f of x0 plus h was, what's the first term? F of x0. What's the next term? H times f prime of x0. What's the next term? It's h squared over 2 f double prime of fact 2 x0. H cubed over fact 3 f triple prime at 0, and so on. Remember that? Know that, because it's not just in differential equations you're going to need that. Need this in all your courses that do any numerical analysis or write down any numerical algorithms. This guy is one of the most important results that get used. Now, I'm perturbing both. It's not just x0 plus h, it's x0 plus h and y0 plus k. Or, in our language, xe plus capital X, ye plus capital Y. How does that expand out? Give me a guess as to what the first term is. Xe and ye, the first. Yes, absolutely. Xe and ye. Now, what do you think is the term? There'll be a term now proportional to x. What do you think his coefficient will be? What was it here? It was the derivative. Now we have a function of two variables. It'll be what derivative? The partial derivative. So it'll be df at xey, it'll be the partial derivative with respect to x, estimated at xey, times x. See, it mirrors just this. But now we're moving the y as well. So what's a term completely consistent with that term? What do you think? It'll be the same thing with y. It'll be plus df at xey dy. In other words, we take the partial derivative with respect to y of f of x and y, estimated at xey times y. Now, there's higher order terms. In fact, I'll write just a few of them. It's 1 over fact 2 d2f by dx squared at xey times x squared plus twice, but it cancels out the fact too, d2f dx dy, xey times xy, and then plus d2f by dy squared at xey times y squared. Okay? But we don't have to worry about that. We are only interested in going this far. So what we're going to do then is near xe and ye, we turn all of these expressions into essentially linear expressions in capital X, capital Y. d by dt of xe plus big X will be just d big X by dt. And then I will just have the first two terms because this guy, of course, because these are equilibrium, this guy is 0. We'll call this guy A and this constant B. And then we'll do the same with the G. So near the equilibrium points, we replace the nonlinear equations by linear homogeneous equations. And you have all the machinery to analyze what they do. And that's what we'll be doing, not exactly next, well, perhaps towards the end of next day. All right, so I want you to go back and revise your Taylor series. Now, in the vector calculus folk, some are taking vector calculus right now, right? You've seen Taylor now with two variables, haven't you? Good. Yes, and they use nice notation like grads, and see, this would be the grad of f times dotted into the, yeah, okay. Very good. So go home.